In this presentation, I'm going to talk about direct proof, and this is one of the three proof methods that I'd like you to understand as part of this class. Direct proof is used for statements which are in the form if P is the case, then Q is also the case, where P and Q are statements that can be true or false. We often write this as P implies Q. Let's have an example. If A and B are even numbers, then A plus B is also even. So here, this part of the statement is playing the part of P. That's what we're assuming. That's what we're given. A and B are even numbers. Given that A and B are even numbers, and this is playing the part of Q, this is what we're trying to prove, that A plus B is also an even number. How are we going to go about this? Well, we're allowed to assume the truth of P. We're allowed to assume that A and B are even numbers. We're also then going to use definitions. So in this proof, we're going to use the definition of what an even number is. And we can also use known truths. What are they? Well, they're things from mathematics that we already know the truth of. So for example, we're going to use the fact that if you take two whole numbers, two integers, and you add them together, you get another integer. We're going to assume that that's the case, and indeed it is. It's been proven by other people, so we're allowed to use it. So let's see if we can actually do this proof. First of all, we're going to use the definition of what an even number is. If A is even, then A can be written in the form 2 times K, where K is a member of the integer set, Z. So if K is a member of the set of the integers, that means that 2 times K is guaranteed to be an even number. So any even number can be written in that form. That's our definition of evenness. So using that definition, we can now try to have a go at the proof. So first of all, we know that A is an even number. So let's write it in the form, say, 2 times an integer, x, where x is a member of the integer set Z. So essentially we're just saying we've got this even number. We know because it's an even number, it can be written as 2 times an integer. We don't know which even number it is, but that's true of all even numbers. So we can do this. So let's let A be written as 2 times x, where x is the appropriate member of the integer set for A. And let's also let B, the other even number, be 2 times y, where y is also a member of the integer set. Now notice I have to use 2 different variables here because I've got 2 different even numbers. They might be the same even number, but that's not being imposed on us. They're just both even and they could be different. So therefore we need to use 2 different variables, x and y. So let's add them up now. Sum of these two is equal to 2x plus 2y. we've got to remember where we're going. We've got to remember that we're trying to show that this thing is an even number. In other words, it accords to that definition there. So in other words, we've got to show that this thing is 2 times an integer, some integer. How can we do that? Well, thinking about that goal, we're saying, okay, we've got a factor of 2 here and a factor of 2 here. We could take that 2 outside and just have x plus y in the bracket here. The reason that we've done that is it looks like it's getting us towards our goal. We've now got 2 times something. All we've now got to show is that that something is an integer. So we write, since x and y are members of the integer set, this means x plus y is also an integer. Let's call it z. Let's call it z. So we're going to call x plus y is going to have a new name, z, and we know that z is an integer. So I'll write that here. Z is a member of the integer set, big Z. So we can write down here that sum is equal to 2 times z, where z is a member of the integer set. What does that tell us about sum? Well, because sum is 2 times an integer, z, that means that sum must be even. That's the definition. So therefore, sum is an even number by definition. That's what we were trying to prove, so that completes the proof, and we're done.